Bismillahirrahmanirrahim. Good morning. Today we will keep going to complete this simple summary to this great article. Article's name is Structure and Electrical Properties of the Calcium 2 plus is the doped element with this parent component, lanthanum, iron, O3. The effective of the A side cation size mismatch and how we can prove these numbers. I'm talking about the column, the mismatch, square mismatch size, and the activation energy, the volume, and we will try to note which one will increase, which one will decrease, what the effect of each other, something like this. This is the first one, the first column, table 1. Here, like I said before, we have 5. We will start from 100% doping of calcium 2 plus. That means at 0 we don't have any doping element. Start from 10 until 40, and we will note the ionic radius average will decrease from 1.36 to 1.35 and 2, and slightly continuously like that from 1.36 to 1.35. And what about the mismatch, cation mismatch? Will increase from 0 to reach 0 when we don't have any compound doping element, and start when started to doping when increase the concentration of doping element calcium 2 plus from 100% until 400%. We will note increasing of cation size match from 0 to 0.36 until 0.96. And we will talk on try to explain some plots in this article. Here, an increase in calcium amount decrease the unit cell volume, and we will see that in the next column. Agrees with the replacement of lanthanum 3 plus, like we know. Here, the authors, researchers, focused on selected to be the lithium as 12 coordinates. We know we have many coordinate number. The researchers selected this number 12, and the ionic radius to lanthanum will be 1.36 angstrom, and to calcium will be 1.35. I can't remember. Yes, with a smaller calcium 2 plus ion with 12 coordinates equal 1.35 angstrom, like I said. Doping the parent compound with smaller ion, doping the parent compound with a smaller ion, what we'll do, will decrease the ionic radius. By that, what will happen? That's mean when doping the parent compound with similar ion, actually ionic radius will decrease, and unit cell volume will decrease. All of them, the ionic radius and unit cell volume. An increase in doping leads to what? Leads to decrease the concentration of the iron 3 plus, specifically iron 3 plus, with larger ionic radius. Larger ionic radius. An amount of impurity. That's mean another element to the compound, which should be dispersed in the mine perovskite phase and the precipitates with low concentration, usually except particle size in the range of a few nanometer, except particle size. Here, this plot explains to us the relation, the reverse line relation between the volume and the mismatch. And when we start to increase, when the mismatch start to increase, we will note the volume will decrease like that. Here at 0 mismatch, the volume approximately 242. After that, at mismatch 0.36, here the volume equal 239. At the last one, at 0.96, here at 96, approximately equal 235.12, but at dot 84 at mismatch equal 235.26, a little bit different between all of these. Here we this column explains to us the relation between the particle size with the doping element concentration, and at the same time with the grain size with the at x-axis with concentration of calcium at y-axis. Here the black ball is indicate to us, explains to us the particle size. It starts from here at particle size. At here at 0 calcium, we don't have any doping element. It's approximately less than 80. Here, when we have 100% of calcium, like doping element, the particle size equal less than 50 nanometer, and start to decreasing like that. Here, at 30 is the bottom point here, plotted here, the lower one at 100% equal approximately less than 20 nanometer. But here we have hysteresis phenomena. At 40, we will note some increasing in the particle size to reach as approximately 30 nanometer. The same thing to grain size at blue. This started from this one at 0 more than 80 nanometer. At blue more than 80. After that at 100% less than 50. And here the blue one to green size, black one to particle size. Particle size. Here all of these results about the particle size will decrease totally from less than 80 until approximately less than 30. But at blue, at grain size, we will note some hysteresis phenomena at 30, specifically at 30, because after that, at 40, we will note some jump, some increase, some different in the results, a little bit different in the results from less than 20 to approximately 30 nanometer at specifically I'm talking about the grain size. Particle size, we don't have any hysteresis phenomena. All of these results decreasing slightly. And here this column explains to us the results about the particle size and grain size. At figure 5, this image reveals that here, by using the scanning electron microscopy or atomic force microscopy, the researchers could to take many pictures to this component's surface. Let me keep going. This image reveals that larger grains are surrounded by smaller ones, and they are tightly connected with each other. tightly, strongly connected with each other. Grain size decreased. Here we will note that in the figure. Grain size decreased from 940 at 0 when we don't have any element like that. When we don't have any doping element, the grain size will record the bigger number, start from 940. After that, decrease a little bit to be 640 at 100%, and like that until the last one will be the lowest number, equal 450 nanometer. I'm talking about the grain size with 30 with 100%. I'm talking about doping concentration. But here at the last we have some change, a little bit change from 450 to 540 in this image. The grain size will increase a little bit to be like that. Here we have, this is important, here we have image explained to us the relation between Lin resistivity divided on temperature and with at y-axis, and at x-axis the reverse of temperature. Here, like I said, here we have 4 concentration of element depending element, yes, from 10 and finished at 40, 100%. What is the doping element here? The researchers used the calcium 2+. Here, started like that. Let me talk about at 10, 100%. Started like that until 5. We will note a little bit change to start acts like a curve. The same thing at 20, but here we will note a clear decreasing in Lin resistivity divided on temperature when increase the concentration of element doping element. Here at 100%, and at the same time the critical point is increased to be from 5 to less than 5.5, and after that change to be like a curve. Here at 30 is the lower one. Here the critical point equal here at 6. No, it's more than 6. 6.2, like I think, or less than a little bit. All of that until 100% doping. The Lin resistivity divided on temperature decreasing slightly by one, but here until 100%, we will note hysteresis phenomena. This one, the green one. Here, the critical point is decreased to be approximately 6. The Lin resistivity divided on temperature increased a little bit. All of these, I'm talking about the reasons, because the element characteristics, like the salt, when you put some salt in the water will be the solvent element. After a little bit, after a while, we will lost the salt in this water. But in the same cup of water, if I put maybe 200 grams or more or maybe less, this solving process will stop until a specific grams number. The same thing with this component, we can benefit from this behavior until 100% of element doping to increase the resistance. After that, this process will be unuseful because the resistivity will increase again. That means we will lose some amount of energy, of current, because that. Here, the plot between, like I said before, resistivity divided on temperature with reverse of temperature. And here, explain to us the continuous are these four colors, explain to us the liner fitting to all of these. That's been a little bit changed from more than 3 until 6 or maybe less or more than. After that, at the 100%, the change started to be clear like that. And the line will start to act like a curve. Now let's talk about the inset plot. Here, like I said before, we have 4 amounts of element doping concentration. Start from 10, after that 20, the red one 30, the green one is the hysteresis one at 400% of element doping. Here, let me say the temperature here started from 125 until 325. The numbers are not clear. Let me use that. Yes, I written that 325 to 125. That's mean we're calling the component. All the samples exhibited strong isolating behavior in which area, in which state at the low temperature. Started from 200 until, let me say, more than 125. Why isolating? Because like we know here, exponentially increasing in the resistivity and the resistance. And at the high temperature acts another behavior. All samples exhibit strong isolating behavior at low temperature. Like I said before, at high temperature, the resistance of the samples changed slightly. At high temperature, the resistance of the samples changed slightly, like that, with a little bit change. And after that, we can say an increase and increase at temperature decreases. What does mean? When the temperature decreases, the resistivity will increase. Like that, it's simple. Here, now we will start to talk about charge ordering and the temperature charge ordering related with it. Let's start. This attribute increase in resistivity might indicate that the samples are charge ordering isolating. This abrupt increase in resistivity may indicate the samples are charge ordering isolating. Some relation between this suddenly exponentially increasing with the charge ordering temperature or charge ordering, and here the charge ordering something like a general with his soldiers. These soldiers can do any action without taking permission because that, let me say this general is the charge ordering. We don't have here anything about charge ordering temperature, but we will try to conclusion that by plot another plot. The resistivity of the samples increase rapidly after charge ordering. That means we have here many different amount of charge ordering. After this charge ordering, the increase in the resistivity will start. Due to why? Due to the localization of electronic states which characterized the charge ordering. What the main reason to this behavior of charge ordering? This is the localization of electronic states. Here, we will try to do simple conclusion about where is the charge ordering temperature. And at first, let me say what is equal charge ordering temperature, equal Lin resistivity divided on T, like that, divide derivation of Lin resistivity divided on derivation of reverse the temperature. Now, here, when we plot resistance at y-axis and the temperature at x-axis to one of these different concentration of doping element, we will see something like this behavior, linear behavior, and after that convert to be acts like a curve. Here we can say the charge ordering temperature and simple where an x-axis near from the spot. It's but not sure. Here specifically we can know where is the charge ordering temperature by this plot all of these. Like I said before, charge ordering temperature equal derivation the length of resistivity divided on derivation reverse temperature. That's the charge ordering temperature. And here at the Kelvin temperature at Kelvin at x-axis, we will note a little bit change here, and after that increase sharply to record a higher amount of charge ordering temperature, and after that increase like that. We can plot a line from the top point at this top and to x-axis. Specifically, this is the charge ordering temperature and this amount of concentration of doping element. Here, the charge order phase can be tricked by three reasons. Can say about charge ordering temperature. Just charge ordering, not charge ordering temperature. Three reasons: temperature, sudden increase in the transport properties of the previous guide, and lattice decrease of freedom. Three reasons: temperature, sudden increase in transport papers, properties, and lattice degrees of freedom. Here we have this column. The first one is no, it's another column. Here talked about the resistivity at room temperature. And we will talk about another element. This is activation energy with these four different amount of concentration from calcium. And we will take a look if we will note another hysteresis phenomena, hysteresis properties like the mismatch at 40 or not. Here at activation energy, all of these results will be increased, will increase from 332 until 276.57. That means will be the largest number at 10, the lowest the lowest amount of activation energy at 40, without any jump between these results. But the reverse behavior we note at 40, 100% with the resistivity at room temperature. Here we will we are seeing jump a little bit from 10.47 to 29.37 on centimeter. Now let's talk about the reason about the resistivity increase, or why while at the same time this compound be a good content. That's relation with the number of holes. When we can increase the number of holes, that's mean the resistivity will decrease, resistance will decrease, and the conduction behavior will increase to be better and better to our develop applications, laptops, and many industry fields. The number of holes will increase. By that, the resistivity at room temperature will increase, but at least 100% of the calcium. That's it. After that, we will not reverse think it's not benefit to us, because at 100% of calcium, the resistivity will increase again. Now let's give a appropriate or simple definition to charge ordering temperature. Is the temperature at which the onset of charge ordering is observed, and it's equal derivation of Lin resistivity divided on derivation of reverse the temperature. Here, let's talk about, like I said before, ion increase to titanium 1.36 to calcium 1.434 as angstrom. The change of the mismatch, ionic size mismatch, even at high doping with calcium 2 plus will be small. Why? Because the ionic radius of titanium near from the result of ionic radius of calcium. Note, using doping element with larger ionic size maybe give high disorder. Using dopant element with larger ionic size may give high disorder at A site, which may lead to collapse, to damage of the charge ordering for this composition. Here some notes. Thermally activated jumping of small polarions is model which describes the resistivity of perovskite oxide. Therefore, the resistivity was analyzed with the use of simple polarion hopping. Here, they noted the simple polarion hopping is an important element in this article, in this process. And some thermally activated hopping of small polarions will be here. According to the small polarion hopping model, the expression for the temperature dependence of the electrical resistivity is given by this equation, resistivity dot. It's different number according to the element. It's a constant, but according or related with which element we're dealing with. Temperature is the absolute temperature. EA is activation energy. KB is Boltzmann constant. Temperature is the temperature. For the small polarions, specifically for the small polarions. Here, the perovskite oxide are classified in terms of their condition mechanism based on the values of EA, of activation energy. Similarly to this few words, when the activation energy is smaller than 1 electron volt, what does mean? That means it's a conductor. when activation energy between 900 millivolts, smaller than 900 millivolts, and bigger than 200 millivolt, between this area from less than 900 millivolt and bigger than 200 millivolt, it's an isolator but from p-type. If less than 200, it's isolator but belong to p-type kind. Here the plot explains us the charge ordering temperature with the different amount of doping element constructions. Here started from 300. Here we don't have 0. Can cancel it. From dot 36 here, 36. We will note the charge ordering temperature equal less than 200 Kelvin. And at dot 64 here, they recorded that charge ordering temperature equal less than 178 Kelvin. Here we have a hysteresis phenomenon. Why? Here at 30, the lowest value, the lowest result of the charge ordering temperature is with 300% of calcium. Equal here at dot 84 equal 160 approximately Kelvin. But when it increased the concentration, when it increased the concentration more to be 400%, what we will note some increasing in the charge order temperature a little bit to equal more than 160. And the insert explained to us the plot of the derivation of ln resistivity divided on T here, ln resistivity divided on T with respect to temperature. At low temperature, we will note sharply increase to be like that. And at high temperature, will change to acts like a line with little bit change, like we noted here. Here, the activation energy at milli-electron volt with the mismatch, cation size mismatch. Here I must say something. When increase the mismatch, we will note the charge ordering temperature is increased, except the last one, increased but a little bit. Here, let's say it's the something, it's happening here with the activation energy. Here at 36, the activation energy equal 332.57. At point at dot 64 here, it's equal more than 310. That means started to decrease. At 30, at dot 84, equal approximately less than 290. And the last one, and the lowest, the smallest amount of the activation energy is 276. That's mean all of these 4 results decreased slightly by step from 332.57 to 276.57, like that, without any hysteresis behavior, any hysteresis results. The electronic properties of perovskite oxide are often crucially connected with the structural distortion around the rare earth side. Here's important a little bit. The electronic properties of perovskite oxide always connected with structural distortion. Electrical properties of perovskite oxide connected, related, depending on the structural distortion around the rare earth. Here, increased p-type carriers cases activation energy to decrease. That's some reverse relation between p-type increasing and or p-type behavior increasing or decreasing with the activation energy, the reverse relation. This reverse relation leading to what? To reverse relation with the energy band gap. Here, now talking about resistivity at room temperature. This compound increased to value 29.47, like I explained before, by using the column. This may be results to we talking about the result, about the jump between the results here. Say until, no, not this column, the first one, 29.47 centime ohm. This may be a result of oxygen vacancy because it's an important element here, and the appearance of impurity phase. Purity phase and the oxygen vacancy. All of these are two important elements in this article, in this compound, and the doping element with compound like that, the oxygen vacancy and the impurity phase. Oxygen vacancy can provide electrons, which compensates some of the holes created. That's mean increase the holes number because the oxygen vacation, because that sure the resistivity will increase more because we have more numbers of holes. Calcium deficiency and impurity has an 100% of calcium in this compound leads to what? Leads to decrease the iron 4 plus ions. As a result, the number of holes, contribution conduction decreased. Here we talking about when we doped 400% of calcium. The situation will different because the holes number will decrease. Why? Because or something depending on another thing, depending on maybe the decrease of the iron 4 plus, that leads to decrease the holes number. Therefore, what will happen when the holes number is decreased? The resistivity is increased. Sure. Here, the structure and electrical properties of nano-sized lanthanum compounds prepared by sol gel. Here it's a conclusion, like I said before, prepared by sol gel method, and to take the pictures to the surface of this complex, they used electron scanning microscopy and atomic force microscopy. It's another methods to take good picture, but to the surface, not deeply. And here the X-ray diffraction patterns where they used it to take this curve at the first slides from the previous lecture. The X-ray diffraction patterns of the samples indicate that all the samples have distorted orthorhombic structure, except at 100% it was single phase. Here, the calcium amount increased increases, both of the activation energy and the resistivity at room temperature of the sample decreased. Here, inverse linear relation between the activation energy and mismatch, cation size mismatch, like I explained by using the last plot, last curve. And that's it. Thank you for watching. You're listening. Have a good day and see you in the next lecture.